Hi there. As we're starting to head toward talking about solutions, I wanted to take a minute to review intermolecular forces in case anybody needs a little bit of a reminder about this. So there's a lot we could say about intermolecular forces. I'm going to try and keep this brief and to the point as much as possible. So the fundamental factor that we are taking into consideration is the interaction between particles that are not bonded to each other. So that means we have atoms and we have molecules. So if we think about the fundamental properties of what makes an atom, the parts that we care about right now are we have electrons in the outer part of the atom, and then we've got this positive nucleus that has protons and neutrons in it. So the two characteristics that we're thinking about are this negative outer part of the atom and then this positive inner part. And so just to kind of review what atoms do when they come near each other, if we have two atoms, and we remember that of course the nucleus is positive and the electrons are negative, then we have two competing factors that are going to be taking place in this atom. So as an atom comes toward another atom, the electrons that are out here in the outer part of this atom are going to be attracted to the nucleus of the other atom, and of course this is happening in both of the atoms simultaneously. So here we have attraction, but of course we also have repulsion happening at the same time because the electrons are both the same charge, and so all of the outer parts of these electrons are repelling each other. And so you've got competing forces of attraction as the atoms are approaching each other, and also repulsion as the atoms are approaching each other. Most of the times the atoms are not going to be getting close enough that the nuclei are repelling, but of course they would too if they get close enough to each other. Okay, so attraction and repulsion are a main kind of idea here. The other thing that we need to think about is what the electrons are like around this atom. And we've had some conversations about the quantum nature of the atoms. And so the way that we want to think about these electrons is that electrons form kind of a negatively charged cloud around the atom. We don't really know where the individual electrons are, if you can even think about electrons as an individual, because they have wave-like characteristics as well as particle-like characteristics. So the easiest way to think about electrons for our purposes is just to think about them as this negatively charged cloud. Okay? So that means that when we have a molecule, we also have a negatively charged cloud where you've got atoms that are bonded to each other. So maybe if we thought about a hydrogen molecule, for example, where we have two hydrogen atoms, and so we've got those two nuclei that are in those two hydrogens, but we also know that this is a covalent bond, so these electrons are shared. And we know this is a covalent bond because it's non-metal, just as a quick reminder there. So those electrons are hanging out, and the characteristics of a covalent bond like that with hydrogen is that these electrons are shared equally between the two atoms that are making up this hydrogen molecule. Okay, so this whole area out here that I've drawn is an electron cloud. So the electrons are just kind of hanging out outside here. Okay, and of course we also have a few background pieces of information that we are remembering, which have to do with atom size. So remember that atoms get larger going down a column, and they get somewhat smaller, usually going across a row in the periodic table. And that means that we have a variety of different atom sizes depending on what molecules we're making. And of course, we also have the total number of electrons and the number of protons in each atom is changing. So we're paying attention to that as well. Okay, and this is all background knowledge for us to keep in mind. So another quick review here is just a review that when we say covalent, we actually can mean a couple of different things. As I said before, these are happening between non-metal elements, and if we have a completely covalent molecule like we did over here with hydrogen, then this is completely shared electrons. But we can also have unequal sharing of those electrons, and we call that a polar covalent bond. And so when we have polar covalent bonding, this is unequal sharing of electrons. And hopefully you remember we had an electronegativity table that I'll go ahead and pull up here for you for just a second. And so when we look at the electronegativity table is giving us a general sense for which elements share the electrons better and which electrons don't share the electrons as well. Okay, so when we are, sorry, we've got a bit of reflection going on here. When we're up here in the high blue, this is a high electronegativity value, and fluorine is our highest electronegativity value on this chart, and it does not share electrons very well. It pulls very hard on the electrons in a bond. Compare that to down here in the yellow. These are having much smaller values, and similarly they are pulling much less on the electrons in a bond. And notice that all of your non-metals here, these pull pretty hard on the electrons in a bond, and mostly the metals do not. And notice, of course, that metals tend to do ionic bonding or metallic bonding, which we haven't talked very much about. But in an ionic bond, the metals are the ones that give up an electron and become a cation. And so this is like an extreme version of unequal sharing, when the electrons are actually given up by these metals and given away to the non-metals, which are pulling much more hard on the electrons in that bond. Okay, so background knowledge some more. All right, coming back to our little flow about intermolecular forces now. Okay, so intermolecular forces in general have to do with the electron cloud here and how those electrons are moving around. Okay, and so we call this polarizability. If you have a molecule that is small and has a covalent bonding, like hydrogen, then the polarizability is small. We don't have a lot of fluctuations of where the electrons are around this molecule. On the other hand, if we have a large molecule, and also if we have unequal sharing already, so we've got a polar covalent bond, and these don't have to happen together. You can have a large molecule with covalent bonding, you can have a small molecule with polar covalent, or you can have a large with polar covalent, so yeah, they can all go together. But if you have large molecules, then you tend to have higher polarizability. And if you have polar covalent bond, then you also tend to have higher, or sometimes we just would say we have high polarizability here. And what I'm talking about in terms of the polarizability comes back to this unequal sharing. So if we think about this electron cloud, and I'm just going to kind of draw a molecule shape. It could be any kind of molecule shape, right? These electrons are attached to atoms that are in this molecule, and I drew kind of a wiggly one right here. If you have a molecule with totally covalent bonding, then most of the time this electron cloud is just kind of uniformly negative in some kind of a small neutral way. But some of the time you are going to have a situation where the electrons randomly go to one side or another. So you might end up with this side over here all of a sudden has a little extra negative on it. And so that means that over here you might have a little extra positive on this side of the molecule. And okay, no big deal, except that maybe you have another molecule over here that's next to it. And if this molecule over here feels that a molecule nearby it all of a sudden set up a positive charge over here and a negative charge over there, then that's going to induce some amount of negative charge in this nearby molecule, which will then create a little bit of positive character on the other side of that molecule, which will affect the next molecule and the next molecule and the next molecule. Right? So this is how polarizability affects molecules and how they interact with each other through intermolecular forces. And so that's what this is showing right here. This is an intermolecular force. The intermolecular forces that we are talking about are due to slight changes that are either temporary because of the random fluctuations of the electron clouds, or permanent because of unequal sharing of electrons. Okay? So this means that we've got several different classifications of types of intermolecular forces. And the types of intermolecular forces have to do with what's happening in the molecule. I'm just going to abbreviate this IMF. Okay? So if we have totally nonpolar molecules, and our quick version of looking at something that's nonpolar we have our different characteristics here. It's going to be nonmetal elements, and it's going to be either all the same element, like H2 or O2, stuff like that, or it's going to be only carbon and hydrogen bonds and nothing else. So if you have like CH4 or C2H6, any kind of hydrocarbon, these are all going to be considered nonpolar. Okay? And if you have nonpolar molecules, these have very weak intermolecular forces because they're always due to just this random fluctuation of the electron cloud. So this actually has multiple names for these types of intermolecular forces, but they are all the same. So they get called London dispersion forces, or just London forces, or just dispersion forces. They are also called van der Waals forces. So there's probably a few. Oh yes, I forgot that one. Induced dipole forces. And let me explain that name here in just a moment. So the dipole, what a dipole is this difference between the negative side and the positive side on this molecule. That is called a dipole. Okay, that's a term that comes from physics, and specifically electricity and magnetism. So the induced part of that is that this molecule sort of spontaneously had its electrons move around, and that induced in this other molecule this shift of dipole. So that's where the induced dipole forces name comes from. Okay, so our key here for these nonpolar induced dipole London dispersion forces and everything is that these are very weak. These are our weakest intermolecular forces, but the other thing that we can pay attention to is that all molecules are going to experience this kind of random fluctuation that we can call London dispersion forces, or whatever we want to call it. Okay, so our next type of intermolecular forces is when we have a polar molecule So again, this is going to be nonmetal elements, and we can go down and think about our nonpolar categories. So we still have non-metal elements here, but if we don't have the same element and they aren't all just carbon hydrogens, then it's probably going to be a polar molecule, even if it's not a really strongly polar molecule. Okay, so something like carbon dioxide, or I don't know, lots of different things, sorry. Okay. So there's lots of different polar molecules, and I'm just, you know, not feeling super creative right now and thinking about a lot of different ones. But what happens with our polar molecules is the same thing that happens with our other molecules, except that they're constantly that way. So carbon dioxide happens to be a linear molecule, and we'll be talking in a different video a little review about Lewis dot structures. So if you don't remember that right now, don't worry, I'm going to go through it in another video. So remember that because the oxygens pull more strongly on the bond than the carbon, oxygen is more electronegative than carbon. The oxygens are out on the sides and the carbon is in the middle. And so you're going to end up with, all the time, some extra negative character around these oxygens, okay, because they're more electronegative. They're pulling electron character over here. And so that means we have a little more positive character around that carbon. And the way that we tend to express this is that we say we have a partial negative charge on the oxygen and we have a partial positive charge on the carbon. And so this is called a polar molecule, and it also has a dipole, and it is a permanent dipole. So it all the time has this directionality of charge that goes out towards those oxygens, right, compared to with the carbon. And that means that if this molecule is around another molecule, whether it's polar or not, they are going to feel this permanent dipole that's on the polar molecule. So that means we have another force here, which is called dipole-dipole forces. And dipole-dipole forces are stronger than those London dispersion forces. All right, so we have a special case of polar molecules, and this is a situation where we have a very strong polar bond. Okay, so this is really just a special case, but we do give it its own category. And in this case, we have what we call hydrogen bonding. And I'm going to be really clear and just call these hydrogen bonding intermolecular forces to try to distinguish them from, you know, like an actual hydrogen bond to something. Because, right, we had carbon-hydrogen bonds here. This is not what I'm talking about. So I'm going to clarify what I'm talking about now in just a moment. Okay. Hydrogen bonding is a special case where we have molecules where we have an oxygen that is attached to a hydrogen, we have, and then something else, a nitrogen that is attached to a hydrogen, and then we also have fluorine that is attached to a hydrogen. And these are special cases because the oxygen, the nitrogen, and the fluorine, these are our three most electronegative elements. Okay, so these ones have the most pull on the electrons in the bond, and they're going to have this strong negative dipole on them, and that leaves this hydrogen with a strong positive dipole. So that means that when the hydrogen, or the negative side, interacts with another molecule, it's going to see an even stronger polar molecule like permanent dipole than regular polar molecules. So we call those hydrogen bonding intermolecular forces. And so an example diagram of this would be where I've got a water molecule, and I'm going to go ahead and draw it in with its angles and everything. The interaction that we're talking about here, this hydrogen bonding interaction. So we've got our hydrogens that have these partial positives and these negatives on the oxygens. and that's every single molecule. Water is a great example of something that has hydrogen bonding interactions. The hydrogen bonding interaction is not this one, it is between these two atoms that are on different molecules. Remember, this whole example, this whole name, this is intermolecular forces. So this is happening between molecules. It's not on the same molecule. And that's really the key. You have to remember that about the hydrogen bonding interactions. It's between two different molecules. Okay? So hydrogen bonding interactions are the strongest of the interactions between covalent molecules. But of course we have one more situation that we can talk about, which is where we have ions. And so if we have a situation where we have ions in a solvent, in a liquid like water or some other kind of solvent that it can dissolve in, then these ions also, these have a positive or a negative permanent charge, right? If we think about sodium chloride, we know that sodium chloride dissolves in water and it makes sodium ions and chloride ions. And so what's happening in there is that these sodium ions are really hanging out with the oxygen parts of the water more than they are hanging out with the other things, the other hydrogen parts, right? And so the sodium has this permanent positive charge, and it is going to be attracted to those partial negatives on the oxygens. And of course the oxygens are also attracted to that full positive charge. And similarly, the chlorides are interacting with the hydrogens who have a partial positive charge. Okay, so these forces are called ion dipole forces. And generally, because the charges on the ions are stronger, they have more electronegativity, or they have more charge, not just a partial charge, but a full charge. These are the strongest of all of these interactions. But the only time that they're going to be happening is when you have, an ionic compound that's dissolved in water. Okay, so hopefully this has been a useful and relatively quick review of intermolecular forces, and please let me know if you have questions about it, and I would be happy to answer them.